yours, yes.
All right. So, Newton's first law says an object at rest will stay at rest. An object in motion will stay in motion unless there is a unbalanced force acting on it. Newton's second law is an equation. Net force is equal to mass times acceleration. So F equals ma. Newton's third law. Anybody got anything? For every action, there is an equal and opposite reaction. So that's a catchy way to remember it. I'm not a huge fan. For every action, there is an equal and opposite reaction. The problem with that is that sometimes it leads to wrong conclusions. For example, what goes up must come down. That's an equal and opposite reaction. That is not Newton's third law. If I hit you, you hit me back. That's an opposite and equal reaction. Equal and opposite reaction, but it's not Newton's third law. Okay? So here's my homebrewed Newton's third law. If object A exerts a force on object B, then object B simultaneously exerts a force on object, exerts an equal force back on object A in the opposite direction. If object A exerts a force on object B, then object B simultaneously exerts an equal force back on object A in the opposite direction. A little bit more verbose than for every action there's an equal and opposite reaction, but here's my thought, here's my hope, my hope is that you won't have to memorize this. You'll just have, for every action, there's an equal and opposite reaction, but you'll be able to apply it correctly. That's my hope. Yep. So, run through some examples. So if you kick a soccer ball, the foot is exerting a force, an applied force on the ball. Question. Newton's third law says, so if object A exerts a force on object B exerts an equal force back on object A in the opposite direction. Okay, so there's a force on the foot from the ball. Now, some people have issues with that. They're like, whatever, the foot that was totally the thing causing the force. Ball's just sitting there. How can it exert a force on the foot? Okay, I agree the fact that the foot initiated everything. However, have you ever tried to kick a ball and then missed? Okay, you are anticipating a force from the ball. The fact that it didn't, this force causes your foot to slow down. If you miss the ball, you're like, whoa, and you're like totally Charlie Brown it. Does that make sense? Charlie Brown thing in childhood still. Okay, Okay. Charlie Brown. Heard of him? Seen him? Yes. Bugs Bunny. Calvin and Hobbes. Ooh, yeah. See, childhood just like evaporates over time. It's just that's true. All right. A person's pushing on a refrigerator. So there's a force on the person from the refrigerator. If all of a sudden that refrigerator would disappear, that person would be like, whoa, and fall over because they're not experiencing that force. Does that make sense? Okay. So there's a force of tension on the chandelier from the chain pulling upward. If you looked at it from the chain's point of view, it's experiencing a force of tension downward, so on the chain from the chandelier. You good with that? Okay. So this last one's pretty crazy. It's a force of gravity on the raindrop. Okay, that's not crazy. What object causes gravity? We haven't specifically talked about it, but it is Earth. The fact that Earth is so massive, it creates gravity, which we'll talk about at the end of this semester or the beginning of next semester. So Newton's third law says if object A exerts a force on object B exerts a force on object A. So there's a force of gravity on the Earth from the raindrop acting which way? Up? That's just weird. Great question. So air resistance is acting on the raindrop, not on the Earth.
So like the chandelier, that's not force of gravity. It's
right. Like it's a yes. Sorry. So that this green force is talking about what the chain experiences because it's holding up the chandelier. Alden.
Would it technically not be acting on it, hit it, or else it would just keep going?
Good question. So gravity is the only example that we know of in this class that is a non-contact force. Gravity still exists even if you're not touching the Earth. So that makes like gravity's still pulling down Okay. Every other force that we've talked about in this class, you have to be in contact with that object to experience the force. So, so if I jump, pretend I jumped, can't really. I am experiencing an acceleration of gravity of 9.8 meters per second squared downward, right? Am I suggesting that the Earth experiences an acceleration of gravity of 9.8 meters per second squared upward towards me? That seemed really weird, and I've never, like, Okay. Is 9.8 the force of gravity? What is 9.8? The acceleration of gravity. Okay. So what I am suggesting is they both experience the same force. Why doesn't the Earth experience the same acceleration that I do? The Earth has a much greater mass. Okay. Does that make sense? So some people might have posed at this point in the time in the lesson, like, well, what happens if, like, we got everybody on Earth together in the state of Indiana, we all jumped at the same time? Could we, like, alter Earth's orbit or rotation or something? Like, all right, so just to entertain that thought, how many people are there on the Earth? 8 billion, 7, 8 billion, whatever. Okay, let's just round that to 10 just for kicks and giggles. Okay, so how many zeros are there in a million? 6. How many zeros are there in a billion? 9. So 10 billion would be 10 zeros. So 1 times 10 to the 10th. You all right with that? Okay, order of magnitude of 10. Let's pretend that every human had a mass of 100 kilograms. That would be roughly 212 pounds. Okay, some people are over that, but most people are not. Okay, so that's how many. So if every person contributed 100 kilograms, now we're to times 10 to the 12th. Good with that? That's how many kilograms the human race would be contributing. The Earth, you ready for this one? 10 to the 24th power. Okay, that's not 2 times as much. That's like adding 12 more zeros. Okay? Every time you add a zero, that's multiplying by 10. And just to give you like a little bit more appreciation for that, like if you had $10 and added a zero, you'd now have $100. If you had $1,000 and I added a zero, then you'd have $10,000, which is a way bigger jump than going from 10 to 100. Added another one, be 100,000. You'd be making way more money than I make. Good with that? Okay. So adding more zeros, so the Earth is like way more massive than everybody on the human race. Okay. All right, so I wouldn't necessarily say write these down. Hopefully these will just come out. So they always have Newton's third law. Force pairs always have the same magnitude. They always have the same strength. They're always going in opposite directions. They act simultaneously. These are the two that people usually we have to like have some conversations about. They always act on two different objects. You've got an object A and you have an object B. So they never act on the same object, and they never cancel each other out because they act on different objects. Okay, and we'll unpack those in this lesson. Good? All right. Give this one a shot. Tell your neighbor.
You're pushing this way. So A's can go that way. B's going that way. B's going that way. No, but that's right. It's the opposite reaction. Pushing that way. A's going this way. It's pushing B that way. B's going to go this way. Yeah. So that's okay. You have to push it as two different objects. So yeah. So what is he? Push A. A's going to want to come back. And A's going to push B forwards, and B's going to want to come back. No. So A's doing, I guess A is equal force. It's an equal force both ways, but because A has greater mass, it's not that compared to B. I know. Wow. Okay.
This isn't pushing, this is spectral. This isn't pushing.
Correct answer is?
This was a G, this was a B.
Correct answer is Dangerous Dinosaurs. Okay. So, Newton's third law. If object A exerts a force on object B, object B exerts an equal force back on object A in the opposite direction. Follow-up question. Have a conversation. Correct answer is? Dangerous Dinosaurs. All right, here's more in-depth explanation than just saying Newton's third law. So the free body diagram of the red You have a force of gravity on the red, a normal force on the red. You have applied force. You have friction. Let's say on the red. You also have a normal force. I'm going to call it a normal force on the red from the yellow. You all right with that? On the yellow, you have, it has its own force of gravity. It has its own normal force. It has its own friction, but it is experiencing a normal force on the yellow from the red. I'm going to call it a normal force, so not to be applied force. Okay. Is the yellow experiencing an applied force from the hand? No. It's experiencing a force from the red block. You all right with that? If you were in line and someone pushed you forward, okay, you'd push on the next person, and they'd turn around, hey, quit pushing! Like I didn't mean, like he pushed. No, you put. Okay, you pushed this person. You experienced the force from them because you would have fallen forward, but really you bumped into them. Okay, Newton's third law would be demonstrated with these two forces. These two forces are not canceling each other out because they act on two different objects. These two forces could cancel each other out. Like if you're going at a constant velocity, this friction could cancel out that normal force. Right, with everybody who's watching phones right now. Good job, Craig. Good job. Okay. Does that make sense? They act on two different objects. They don't cancel each other out. Only forces acting on the same object can cancel each other out. Same question. I'm just flip-flopping the order. Tell your neighbor. Come on. Mm-hmm. Correct answer is D, dangerous dinosaurs. Okay. It'll be a different amount of force compared to the last scenario, but the force that A experiences will be the same force that B experiences. Okay. Okay, here's a little more life applicable scenario. Tell your neighbor.
What do you guys say? Yeah, I think that that's standard focus. Logically,
Okay. Correct answer is C, the same force. Why? Newton's third law. Follow-up question. Same scenario. What is the acceleration? Who's experiencing greater acceleration? Tell your neighbor and tell them why.
Acceleration for stopping, or like when they collide, like which way?
During the moments of impact.
Like when they collide, stopping faster. I was gonna say the Volkswagen. Well, Volkswagen's gonna stop and get dragged by the mass. Oh, and the impact. Yeah, definitely the track. Or safety greater.
Okay, what do you say? A's on the table. All right. When I was in your shoes, I came to the conclusion real fast. It's the same force. Just because the teacher said so. And I'm just trying to I didn't really believe it. I was just like, okay, same force. That's what's okay. Until I saw this demonstration. So,
If I'm right, it is logical.
borrow your desk.
They have a head-on collision.
Okay.
I'm also gonna guess by the fact that there's a buffer there that
Okay. Here I've got a force probe on both things. So I've got Mack truck here. Okay, Mack truck's here. Volkswagen Bug is here. So when I press collect, I can exert a force. So this is the Mack truck. This is the Volkswagen Bug. Okay. So what I'm going to do is I'm going to go through a series of collisions. I'm going to do Volkswagen Bug at rest, Mack truck, boom. I'm going to go Mack truck at rest, Volkswagen Bug, boom. I'm going to do a head-on moving collision, both of them moving, boom. Okay. I'm going to do one where the Volkswagen is pushing, And then the other one where the Mack truck's pushing, I'm going to push, push, push. I'm going to do as many combinations as I can in 10 seconds. Okay? Sound good? Okay, here we go. Head-on collision with Volkswagen Bug. Bug smashing. Both moving. Boom. Pushing, pushing, push, 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 push.
The same.
Okay. If you notice and be in awe of how symmetric this looks. Okay. In each collision, both the Mack truck and the Volkswagen Bug experience the same force for the same amount of time. Okay. In the interactions, they might have had different amounts of force depending on the scenario, but both objects will always experience the same force for the same amount of time, always. This demonstration sealed the deal for me. I'm like, okay, it is. It really, truly, like, we just measured it. Good with that? So, is it a good idea to lock horns with a Mack truck? It's the same force. Okay. Which experienced a greater acceleration? A. Why? Has less mass. Both vehicles experience the same force. We just established that. But how they respond to that force is determined by how much mass there is. Here, the Mack truck has a lot of mass, has a lot of inertia, and its acceleration is smaller. Versus the Volkswagen Bug has a little bit of mass, therefore it has a lot of acceleration. Good with that? Holden.
So what if they intentionally made it to where they were going the same speed, so they had the same acceleration?
So they won't have the same acceleration. They would have the same speed, initial speed, but if they were going and they hit, the Mack truck would. Does that make sense? So they wouldn't come to rest. Okay. Give this one a shot. Okay. If you've ever shot a gun, there's a kickback or seen movies. Okay. Which one is experiencing a greater force from the explosion, the bullet or the gun? Same. Newton's third law, right? So why does the bullet go flying and the gun just stays put? Because the gun is more massive and held by you, which is massive. The bullet is not massive. So if you made a very small, massive, or small or lightweight gun, you've got two bullets going on. Does that make sense? Okay. So yeah, dumb idea. B. Okay, I'm trying to come up with scenarios of what everybody's questioning. Like, well, yeah, but what about? Correct answer is the same. Okay. So how? Why is it? Why does the board break? So Alton.
So, because it's exerting the same forces that way, it hurts when you hit a board.
That is why. So the force that you're exerting on the board is the same force that the board is exerting back on your hand. The reason the board breaks is because the force that you exerted is greater than the molecular bonds of the board could withstand. If I hit a fly, it experiences the same force that I experience. The fly's body just isn't strong enough. I just feel a little nudge. The fly. Okay, does that make sense? Last question. This is a good question that you might want to pay attention to. Tell your neighbor what you think. Okay, correct answer is false. Okay. Okay. There has to be two objects. These two forces are equal. Yes, they are going in opposite directions, but they're acting on one object. They're canceling each other out. There's a normal force on the book from what? The table. Therefore, Newton's third law says there has to be a force on the table from the book. There are two different objects. These two are Newton's third law. There's a force of gravity on the book from the, what object is creating gravity? Earth. Therefore, there's a force of gravity on the Earth from the book pulling the Earth upward. Okay? Newton's third law has to act on two different objects. Got a review worksheet due tomorrow. This will not be on the test, on this test, but on the next one.
I'm still really confused.